It's all yours.
Brilliant.
Okay. Hello, everyone. Can you hear me?
Yes.
Cool. My name's Johnny Klein, and you are at Little Talks on Big Ideas. And we do this once a month. This is our first time at Union Hall, so thank you for, we had a venue shift, and we're glad to be here. And just by show of hands, how many Invisible City members do we have here? 1, 2, cool. Nice. Myself, Luke, you Invisible City member?
Yeah.
Okay, cool. How many Coloradans do we have here, live in the building here? Yeah. Yeah, so this building is called the Coloradan. Cool, thank you for coming. And then how about from the illustrious men's discussion group? How many people do we have there? Oh my gosh, look at that, that's amazing. Cool. So what we do with Little Talks on Big Ideas, what we try and put you in touch with people that are operating on the edge and maybe to change what you deem possible. And so we finished up a 3-month speaker series on the outdoors. We had it was really great. We had people that had climbed Everest. We had we had a CEO from the ski industry and how it's leading in a male-dominated industry. We had a speaker on orienteering, the sport of orienteering, and now we're kind of getting into the physics speaker series, and tonight we're launching that with astrophysics. Hopefully next month we'll be doing a talk on quantum mechanics, quantum computing, quantum navigation, and what's going on in that space. So we try and do these once a month. I'm not sure where that one will be, but stay tuned. So before we get started, I want to, and by the way, my name's Johnny Klein. I am a member of Invisible City. I'm a resident of the Coloradan, and I'm a board member of Union Hall, along with Crystal, who's also on the board, and an Invisible City member as well. Before we get started, Jess.
And technically a Coloradan.
A Coloradan, but not a Coloradan resident. Yes, you're right. Jess, could you just share a little bit about Invisible City for us? Yeah.
I don't know if I. Okay.
Yeah.
Sure.
Go for it.
Invisible City or Union?
Oh, sorry, Union Hall. Union Hall.
We already did that. Hi, I'm Jess. Currently, I'm the gallery marketing manager of Union Hall. We're a nonprofit art space that supports new and emerging artists and creators. We rotate art exhibitions as well as have like all sorts of art adjacent events here year round. And right now, this in this space is a solo show by a local poet, artist, and musician, Diego. And after the presentation, we'll lift the screen and kind of turn on more of the lights on so you can actually see the sport if you want to hang out after that. And back over to Yanni and Luke for their little talk about big ideas.
Thank you. So I'm going to quickly read Luke's bio here, and welcome, Invisible City members. There's beers back on the platform over there. So Luke was born in Denver, and he spent his life under the inspiring skies of the Rocky Mountains with a degree in physics and astrophysics from the University of Colorado. He started his career by diving into research on active galactic nuclei. But it was working with renowned observatories in Western Australia that sparked his passion for astronomy, education, and storytelling. After returning to the U.S., inspired, Luke realized there was an opportunity in Colorado to bring the magic of the cosmos to those eager to connect with the universe, and found astrotours.org. Today, Luke combines his scientific background with his experiences to create unforgettable stargazing adventures and welcoming people to discover the night sky. So welcome, Luke. Tonight we're going to talk about time and space. And when I was setting this up with Luke, I said, are we going to talk about space-time? And he said, well, we're going to talk about time and we're going to talk about space. So he'll get into that. And the format tonight is we'll have about 45 minutes of a presentation from Luke, and then about 15 minutes for Q&A. And we'll try and honor your time and get you out of here by 8 o'clock. So we'll just kind of go really fast. But in really amazing Invisible City tradition, we don't do anything normal really there. So we kind of have a little fun little quick Q&A for you. And I'm going to ask you questions for about 3-5 minutes. And you just, the first thing that comes to your mind, tell us. And this is to get the audience to know you. Luke has not seen any of these questions. He has no clue what's going to come to him on this. But here we go. You ready? I'm going to pass the mic back and forth because the other mic went down. So what's one of your favorite flavors of ice cream?
I'm feeling like mint chocolate chip right now.
Cool. You can keep that. What's your favorite color?
I like the palette of the Aurora Borealis. So those like purples and greens that are like almost neon or neon adjacent.
Any siblings?
Yeah, my sister right here. Even a little.
What's her name? Give her
Maya.
a plug. Maya. Cool. How would your closest friend or family member describe you?
I don't know. Do you all want to take
No.
this?
Yeah.
This is my mom in the front row too. I feel awkward speaking for her. When she's
you got to go for it. First thing comes to mind.
Of course, the best, but not better than my. Probably a hedge of.
Nice segue to the next question. Are you competitive?
Yeah, I'll compete.
Yeah.
Cool.
Thoughts on pickleball?
Oh, is this you asking me to play pickleball with you? Or?
No, I'm just. What are your thoughts?
I've played it once, and I'd say I'm for it.
Got it. What outfit do you feel most comfortable wearing?
I have a little spacesuit, yeah. I wouldn't say I feel the most comfortable in it, but I definitely wear it like when I go skiing and stuff. It's fun.
Does it say NASA on it?
Oh, I do have one that says NASA. Everybody asks if I work for NASA, and I have to tell them no, we're like a competitor of theirs.
What do you fear?
I guess the aliens, if we're on topic. I think they're,
Are you a procrastinator or a planner?
Well, both. I guess it depends on how stoked I am for the thing.
Are you stoked tonight?
Yeah.
Okay, good.
I had this slide ready
Okay.
Friday, and we planned this Thursday, so that was pretty interesting.
What was your backup college?
Backup college? I remember we toured Berkeley, I think. I'd say Berkeley.
Not too shabby.
Yeah.
Do you think I'm objectively handsome?
Yes.
Let's see here. What place do you love to travel to?
Australia. I've had that in
that's part of your story that you're going to get into.
Yeah.
Are you enjoying this right now?
I'd say the questions did loosen me up a bit. I was feeling a little bit more nervous.
Okay, cool.
Yeah.
And with that, guys, Luke.
Well, welcome everyone. The Luke as mentioned, we have. I was going to do a whole little intro about me, but since Johnny already did that for me, this is the renowned observatory in Australia. I was working for this guy. He's a bloke who goes by the name of Space Gandalf, as you can probably see why. He's kind of an Australian public television personality. He has a little show where he teaches the Aussies what to look out for in the night sky. He also does little programs where he takes folk out to the bush and shows them the stars in his giant telescopes. And I absolutely loved it. It was my favorite job ever. So once my visa expired, came back to America, I looked all over for a similar job and couldn't find anyone else doing them in the States. So figured I'd make a go of it myself. It's been about 7 years now. It's really unfortunate is Space Gandalf did pass away earlier this year. I got to go back to Australia in July. He was a big surfer, and they had a traditional like surfers paddle out for him. And his daughter met me there, and she wants to have me come back and try to get it going again. So that's going to be in June. Hopefully I'll be going in and trying to set his telescopes back up out there. But yeah, this is a little overview here of what we're going to go through. Basically, all of the universe as much as we can get to it. And here I'm pretty short on time for making that happen, so probably just jump right in it. Although I would point out do feel free to ask questions and stuff as we go along. Like that's what this is a live program. It's not like you're watching a TV show here. Like you can definitely let me know if something's a little not explained to the amount you need here. So let's just jump into it. So first I'm going to start with like a little bit of stargazing tips and stuff. So this one's really important, is the twilights. So there's 3 levels of twilight. There's secretly a 4th. If you're a photographer, you probably are looking for the golden hour, which is when the sun's between 5 degrees above the horizon to the horizon. That's when like the sun's perfect for photography. For astronomy, we care about when the sun's below the horizon. So when it's 0 to 5 degrees below the horizon, it's called civil twilight. That's usually when I'm like, do I turn on my headlights or not? Like technically the sun's set, but it's still bright enough to see and do anything you would during the day. And when the sun's between 5 and 10 degrees below the horizon, that's called nautical twilight. Same story for ships at sea. That's when they're turning on their lights, their radars, radios for nighttime navigation. Then when the sun's between 10 and 20 degrees below the horizon is astronomical twilight. And that's what astronomers really look out for. That's when we have the dimmer stars start to come out and we can really see the stars. It's I'd say about an hour after sunset. It definitely depends a lot. Of course, with winter time, the sun's going to go below the horizon a lot quicker just because sun's not over this side of the hemisphere as much. And then in the summertime, yeah, it's pretty wild, like in the middle of July when it's like 9 and it's still pretty bright out because the sun's like technically set, but it's still can still see in everything this far north. Light pollution is another big consideration if you're going stargazing. We're of course right in this red dot there, which I say don't let that discourage you. Like people are often like, I need to find the certified dark sky before I look at the stars or whatever. But even if you're just out on the deck out here, out in the street, you can easily see the moon and stuff. And then it all just is kind of how motivated you are. You can see this little orange bit, that's City Park. That's where I go often, even for just meteor showers and stuff. You can catch a good amount of them even in town, and it's just like 7-10 minutes from here. If you got 30 minutes, you can go to Cherry Creek or the Arsenal or somewhere outside of Golden or Boulder easily. And then if you have about an hour, you can get up to Loveland Pass or anything around here. Like it's definitely really nice when communities do commit to a dark sky regiment kind of thing to get that certification. But it's not as rare as that makes it sound. I just use this website, lightpollutionmap.info, and you can just drop down here, get the newest data from a NASA satellite that's looking at where all the light pollution is coming, and that's, I think, the best way to find a really dark sky around you. All you need to stargaze is just your eyes. Like I was saying for the meteor showers, it's actually better just to use your eyes rather than having a telescope or binoculars, because the best thing to do for a meteor shower is lay out underneath the stars and get as much of the night sky in your field of view as possible, because it's very random what part of the sky they'll come up in, and so just your eyes is all you need. I would say red light helps a bit. So you have your night vision takes about 20 minutes to gain. You lose it instantly looking at white light. So if you have like a headlamp or just a flashlight that you put a little red film over, that helps a lot in preserving your night vision. It takes you 20 minutes to gain it and you lose it instantly looking at white light. So red lights are helpful. Then the apps too are definitely another very easy step to start stargazing. There's tons of apps out there. I recommend Star Tracker and Sky Safari as kind of more the ones I use, but if you just go online or on the App Store and get the top like 5 or whatever ones, however many you can download. They'll all teach you something new. Some are better for the constellations, some are better for the planets. There's one called Aurora Alerts that will give you like about a 3-hour warning when there's going to be good auroral activity where you're at. So that's plenty of time to get up to Loveland Pass or something to go check out the aurora. There's one called Heavens Above if you want to identify satellites. There's, like I said, tons of apps, and each one will teach you something new. Then if you do want a little extra, I usually just recommend start off with a pair of binoculars. You'll be amazed at how much you can see with a pair of binoculars. I actually brought these. These are probably way more overkill than you need. You probably have some at home that you can use. They're on the tripod up there. But yeah, I was expecting to see the moon tonight, but I think that was, it's overcast and there's not really a good space to do that. But it's a good, you can check it out, point it at the trains as they pass and like really see in there. But yeah, if you're looking at binoculars, those are 20x, which you'll see are very hard to use if you don't have them on a tripod. I recommend between 6 and 15x. 12x is about perfect for the zoom on binoculars. Then aperture, those are 80. Again, they're so bulky that I just use them on the tripod all the time. But I'd say 40 to 60 is about where handheld binoculars are. 40 is like something you could put in your backpack. 60 is more something you'd like put in your car or something, and whenever you're somewhere dark enough, you can get them out. And so 50 would probably be a good middle ground there. But usually I say that, and people are still like, what telescope should I get? Should I really steer people towards the binoculars? Because all the telescopes I own, almost all the telescopes I own, there's a very few exceptions, I buy on Facebook Marketplace, and all of the stories are exactly the same. Grandma got it for the grandkids. They used it once, maybe twice, and it sat in the garage for the last decade or two. Someone's cleaning out the garage and puts it up on Facebook Marketplace, and I buy it up really cheap. So I think binoculars are a good way to see. I'd say I'm around 40 right now. I mean, they're owned by Astro Tours, so it's like I don't know if that counts, but yeah. It's also, if you do upgrade to a telescope, it's nice to have the binoculars on hand to see where you want to point the telescope. But usually people are still persistent and say like, but really, what telescope should I get? And so these are the two that I recommend. The Dobsonian, the question becomes, how dark is your backyard? If you live in Denver out here, you're gonna want something more portable, like the Mac Cassegrain. This was actually one of my first telescopes. I got it when I was like 12 or so, and it's super portable. It fits in basically a suitcase, and with that little telescope going all the way into like the backcountry in Rocky Mountain National Park, I can see so much more than if I set up my big telescope in my backyard here in Denver. This is the Dobsonian. The Dobsonian, you can see, is just big and unwieldy. That's my biggest telescope. And it looks all complicated with the truss rod system because that one folds down a lot. But they make them really cheaply. You can just get, you can make one at home. I recommend Dobsonian so much, people tend to think I have a stake in the company, but I don't, not more than anyone else does, because the name Dobson comes from an inventor. He was an inventor or tinkerer, in the 70s, and he was just working in his garage trying to build a giant telescope. And this is the design he came up with. And if you're a maker yourself, you can probably size it up. When you get down to it, it's just some plywood and a tube. That one, like I said, is a little complicated with the truss rod system, but I've seen them made out of just a cardboard tube and some particle board super cheaply. That's what Dobson wanted. Rather than getting rich off of his idea and patenting it, he put it out into the world so anyone could make a Dobsonian telescope. So for the same price as this small telescope, you could get a Dobsonian, so that style telescope, the same size as the bigger telescope that's in the background in that picture. The main thing is it's just big and unwieldy. So if you don't have a good backyard, you're not going to want to take that camping with you. Like, it's much easier to sell to just sneak something like this into the back of your friend's car rather than telling them all while you're going camping, like, make room for something bigger than I am with a bigger one like that. But yeah, now can get to stargazing. And before I like to get too much out there, I like to start with what's down here with our planet, with the Earth. So a couple reminders here. Reminder number one, the Earth is round. Everyone's still awake here. I do these programs for the Girl Scouts, and I did have one little girl give me this correction, that the little fine print, that it's actually an oblate spheroid, which means it's a little flattened on the poles, little bulging on the equator. Yeah, that girl was definitely earning her badge that night. And also the Earth is turning on its axis once a day. So I call these reminders because it's not like, whoa, mind-blowing information right out the gate here. But I feel like it could be, or it should be. Like right now, we're all on a journey around this planet. Once every 24 hours, you do a complete lap around the globe, and you don't even have to get out of your bed to make this journey. But I feel like because we live indoors and work indoors and spend so much time inside these days, we don't really get to make ourselves part of this journey. We don't really get to see this happen. If I were to ask you right now, would anybody know what direction the Earth's turning? What direction the Earth's taking us on this journey? Yeah? I have a hint here. So the big hint is the sun sets in the west and rises in the east. So this is a solid hint. It's a 50-50 shot now. I'm definitely fishing for one of those two directions. I also love this hint because those words are over 400 years old. And 400 years ago, people are getting burnt at the stake for talking about this kind of movement. It wasn't well understood that as the sun comes up or the sun goes down, it's actually not the sun that's moving at all. It's the Earth turning away from the part of the sky the sun is in that makes it appear that it's going down. Which is definitely a way more long-winded way of explaining it, way more romantic to call it a sunset. But I feel like if we could update these terms to reflect our modern understanding, everybody would be onto it right away and say, of course, we go to the, anticipation here, to the east. So yeah, right now we're all doing about 900 miles per hour. Roughly that direction. I don't really know downtown with the streets all. We have someone pointing that way and that way. I did look it up before. The mountains are that way, aren't they? Yeah. I feel like it's roughly this direction. I did look up before I got here. The Capitol building is about, it's just under 2 miles from this location. So 2 miles at 900 miles per hour means once every 18 seconds you occupy this bit of space that the Capitol building was in just when I started the sentence there. So yeah, if that doesn't have your head spinning and feeling it already, it's all right. That's the main thing that I want to get through here. So this is the daily rotation. So basically every 4 minutes we turn just 1 degree. So that means if there's a star right on your horizon, in 4 minutes that'll be 1 degree above the horizon. You can see like the time lapse that was playing on before this, and this little time lapse here, this is of an observatory in Chile. You can see how the stars move over time, circling around, and that's all just the Earth's turning. I feel like usually I go through this in my programs where I can actually like show people the stars and stuff. I'm definitely more of a show me learner than tell me, so this is a little different way of going about this, but I feel like adding in the next line there, the yearly rotation, makes this make sense a little bit more. So I'll try to go through both of them at the same time here. Basically, there's 365 days in a year, which works out perfectly because there's 360 degrees in a circle. So that means every day we shift around the sun just 1 degree, which means every day you'll see in the sky the stars shift just by 1 degree if you look at it at the same time of night, every night. Which 1 degree is really small, you're never going to really see that, but 1 degree a day over the course of a week ends up being 28 minutes or almost half an hour. So you'd see a half-hour shift, and I was trying to shoot to be at the half-hour mark of the program here when I introduced this, to say that if we did this again in a week's time, the sky we have right now would be the same sky as when you all arrived here at the event. I sort of say a week's time because I feel like that's a reasonable amount of time to kind of remember this and like check back in on it. And you will see the Earth turning in a week's time. Where it really clicks for me is at the month, a month being 2 hours. That just, that's easier for me to hold on to, just something about there's 2 sets of 12 hours in a day and 12 months in a year. It kind of makes sense that each month would hold 2 hours. Why that really clicks for me is the program I normally run outside of Boulder is a 2-hour long program. So it works out perfectly that this sky I'm starting with that program is what I was finishing the program with a month prior. And what I finished the program with after those 2 hours is the sky that I'm going to start the tour with a month after. Then I also feel like it just gets really simple once you go a lot bigger. So 6 hours being 90 degrees or 3 months, that makes sense because those are each 1/4 turn. So it would be 90 degrees. So if there was a star directly above your head right now, in 6 hours or 3 months, that star would shift 90 degrees and be right on your horizon. 12 hours from now, 12 hours is when you spin upside down, basically. You're going to go one full rotation around the planet and be hanging upside down from where you are. So if you lock a laser like on a star right above your head for 12 hours, you have to point directly below your feet. And then 24 hours or 1 year is, of course, one full rotation. So you'll be back exactly the same point as when you started observing if you do your homework and watch this throughout the next year here.
Are you really at the same point? Solar system moving?
Yeah, so yeah, it depends a lot on your frame of reference, which I have a slide on that, but I think I have one more slide before we get to that, and that's the missing middle between these two. So this gives us the day, the Earth's rotation, and then this gives us the year. And what would, well, this is still going with the year, but I'll get to that in a second. So again, I'm definitely more of a show me than a tell me kind of learner, so I tried to put all this clip art together to try to explain what's so easy to just point out in the sky. But if you're familiar with the Big Dipper, most people are, that's probably the most iconic constellation of the Northern Hemisphere. Next time you look at the Big Dipper, look at these 2 stars at the end of the vessel of the Big Dipper. Those 2 stars are called the pointers because they point at the North Star. So if you follow a line straight along from those stars, you will hit another star. It's dimmer than these 2 stars. People often think the North Star is really bright. It's a fairly dim star, actually. But it is definitely on this line, and it's the brightest one on this line if you just follow it north until you reach the North Star. Something else that's handy about these 2 stars is they're almost exactly 5 degrees apart. So this is a little handy method of getting your latitude is if you hold your hand out at a forearm's length, see how many fingers you can fit between these 2 stars. For me, it's 3 fingers. It's usually about 3 fingers for everyone. So now you know that 3 fingers is 5 degrees. And to find your latitude, the North Star is always going to be as many degrees above your northern sky as your latitude. So you can just stack those fingers on top of each other, reach the North Star, and that'll be your latitude. So if you're familiar with a road called Baseline Road in Boulder, Baseline Road is actually called that because it's surveyed to be right on the 40th parallel. So if you take Baseline Road all the way to the mountains, it turns into a windy mountain road called Flagstaff Road. If you can stomach all those hairpin turns to get to the top of it, you'll see Baseline Road cuts a straight line all the way across the land. It stops for lakes, but picks up exactly where it left off on the other side of the lake. It actually goes out and becomes the Kansas-Nebraska borderline road eventually, because that's also surveyed to be on the 40th parallel. So we're a little bit south of Baseline Road down here, of course, but it's not, if you're just measuring with your fingers, it's about what you get. Also, another thing with this, your horizon is like, imagine you're on a boat where the ocean's horizon would be. You don't want to be starting from the top of a building or a car or anything like that. If you want it to be super accurate, you hang a plumb bob and what's 90 degrees from the plumb bob. But I think if you're just measuring with your fingers, again, it's just imagine where the ocean horizon would be, and that'll be close enough. But is everybody good with this? You got your navigation down, ready to find your way home tonight? Sweet. So why I wanted to get through all of that is because the Big Dipper really shows you your seasons. The Big Dipper has been used as a seasonal indicator for centuries here in the Northern Hemisphere. So I was talking about how every 3 months, basically, we turn 90 degrees. Well, you can see how that works here with the pointer stars. The pointers are kind of like the spokes on a bike wheel. They're all pointing to that center hub of the bike wheel. And so as the Earth rotates, you'll see the Big Dipper go circling around that North Star, but those spokes will always keep pointing to the North Star. So you can use it as a little calendar in that way to see how much of the years passed and how much of the nights passed. Because if you watch this angle shift around the North Star, like I said, 30 degrees is every 2 hours. So yeah. Then next is the moon. I added this because we covered the day and we covered the year, but the missing middle is the month. And this is actually where we get the month, is from the moon. If you break the word apart, it's moonth. So the moon with the suffix th. Suffix th denotes a measurement, so like 1/4 or 100th place or whatever. One measurement of the moon is roughly phase to phase of the moon, so full moon to full moon. Our calendar is a solar calendar. It's not really linked to the moon as much, so the month doesn't really work out as it should in it all the time, but it's roughly there. And then I have this little dance that I usually can't do at the astronomy nights because it's too dark, but I thought it would be a good demonstration here. So I'm going to play the role of the moon here. This telescope here, or the binoculars here, is going to be the Earth, and y'all are all going to be the sun shining on me, just like this spotlight. So the sun right now, if I was the moon, is illuminating my full face. We're at maybe just before full moon, so it would be roughly here where like a little bit of my face is in shadow. But let's just say it's a full moon right now and my entire face would be in the spotlight here. 1 week from now, the moon shifts a quarter way around the Earth. So it does one full rotation about every 4 weeks. So every month is about 4 weeks. So 1 week from now, it's going to shift 90 degrees. This is how you can see this side of my face would be in darkness. This side is illuminated if you were on the frame of reference of the binoculars here, which are playing the Earth in this little dance I'm doing. 2 weeks from now, 1 week from then, the moon's going to orbit around here. So the backside of my head is now getting illuminated. So there's no such thing as the dark side of the moon, unless, of course, you're a Pink Floyd fan. It's the reverse side of the moon, which gets light on new moon. 3 weeks from now, 1 week from then, is when the sun's going to be illuminating the other half of the moon's face. So here on the Earth, you'd see this half of it illuminated, this half in darkness. And then 4 weeks from now, 1 week from then, the moon will be roughly back in its same position, so fully illuminated. So you saw I turned my back to you. The moon actually does do one rotation from the frame of reference of the sun. It only looks that it's still to us because our frame of reference, as the Earth, it orbits the Earth at the same speed as which that it rotates too. So 1 day on the moon equals 1 month. What?
Here, 1 month here.
Yeah, one month from Earth's frame of reference would be 1 day from the moon's frame of reference, roughly. Again, our months aren't exactly lined up. Yeah, it's all relative. But yeah, everyone have the moon. Yeah.
Really quick, because I know there is a mini moon right now. I mean, that happens every once in a while. How do you track those?
That's more of like
They're not really mini.
what's that? Oh, she was asking if there's a mini moon right now. How do we track the mini moons? So the mini moon is a captured asteroid. Basically, the orbit of the moon and the Earth that I just did was really simplifying it because also the sun's moving, which was your question earlier and what we're about to get to here. But since the Earth's going around the sun while the moon's going around the sun, it's very complex gravitationally. It's actually called the three-body problem. Just like the Netflix series, it's actually after a problem in physics where it gets really hard to calculate the orbits of three bodies because they all interact with each other very differently. Another thing that they usually use as an example is the chaotic pendulum. If you hang a pendulum off of a pendulum and you drop that, the first pendulum we know is just going to go side to side. But you put another pendulum on it, that pendulum's going to go like all crazy different direction, and every pendulum down gets harder and harder to predict. So the mini-moon, they only have predicted out a couple months or so. They know it's not a stable orbit, so it's not going to stay with us like the moon is, but they know that it's going to come in and orbit Earth a little bit and then leave. Yeah, and the mini-moon, it's not like you'd see just a smaller moon or anything. We're talking like an asteroid or so. Like, I have a computerized telescope that's happy enough to pull it up, but it's just like you look at a little dot in it. It's not like, you just have to kind of trust the computer is pointing at the right little dot in the sky. Mostly is interesting watching it over the course of a couple weeks, seeing it move amongst the stars, just like the moon. If you watch the moon over the course of a week, it'll move amongst all of the signs of the zodiac, actually. So the signs of the zodiac are actually, it's the fancier term for it is the ecliptic. It's a plane that goes around our sun. If you think back to school, how they show you sun in the middle and all the planets and that flat disk around it. Because all the planets orbit the sun in that flat disk, they only pass through the same 12-ish signs in the zodiac. And that's also, I'm sure, what this is measuring too. Each time, if you watch the moon over the course of one night, it'll look like it's moving with all of the stars. But if you watch it every night, you'll see it shifts in the sky just between each zodiac just a little bit. It covers all 12 zodiacs in 1 month. But yeah, now this is getting to where it moves a lot more, where the sun is orbiting the galactic core. So we did the day is the Earth's rotation, the month is the moon's rotation, the year is Earth's rotation around the sun. So now if you want to zoom out, there's also a galactic year, which is when Earth goes around the central core of the sun, of the galaxy, and that happens once every 225 million years. So it's just not like something we use in our human lifespan. It's not like something that we really interact with. But again, the Earth is billions of years old. So the Earth's done this rotation many times. This is artwork by Phil Lewis. He's an artist out in Boulder. And he put jellyfish above the Flatirons. And he said it was because when the Flatirons were deposited, this was all an inland sea. And so he was just imagining the jellyfish hanging out above the Flatirons when he was on a hike up there. The joke I always make, this is a poster of the infamous Fish concert that got Fish banned from Red Rocks. That if you went to Red Rocks one galactic year ago, it would all be Fish concerts because there'd be nothing but fish there. Oh yeah. Then now I'm going to go just move up the scale. This is another thing that I never really get to talk about on my programs in Boulder because it's dark out and I can't really show people the like kind of scale that we're going. So we start with the moon. The moon's the closest thing to us. It's 250,000 miles, and that's the last distance I can kind of hold in my head as far as miles, and that's just because the car I owned in Australia, actually, the camper van, had over 400,000 kilometers in it. So I'd always joke that it was on its way back from the moon. So yeah, 250,000 miles, it's kind of what you can expect to get out of a car if it's decently well built and well maintained. You can get usually about that from it. But that's really the last distance I can hold in my head as miles because that's a big frame of reference. The Earth to the sun here is 29 million miles. So, 92, sorry. 92 million miles. So, yeah, I can't even fathom that. But that's where this little unit comes in 1 AU. So you can see, or is it Earth is 1 AU from the sun. So this is how I like to make like a little solar system in your mind. The scale of the solar system is if you shrunk down the Earth to be the size of 1 millimeter, 1 grain of sand, that grain of sand could fit in the palm of your hand. The moon's about a quarter the size of the Earth, so the moon would be a quarter size millimeter grain of sand, a smaller grain of sand, about 1 1/4 inch or in the same palm of your hand. The sun is about 112 times the diameter of Earth, so the sun would be 112 millimeters. That would be about the size of a grapefruit or so. And this AU means that if you set it's just whatever you set that unit to be, it just works out because it's the Earth-Sun distance. So if we use that as our frame of reference going forward, it makes it super easy. So I like to say it's 1 AU is about 10 yards. And at this scale, it works out pretty well. It's actually about 10 meters at this scale, so a little bit more. But yeah, if you say Earth's on the 10-yard line, there's a grapefruit over by the coat rack there, maybe the back row there. They would be on the 4-yard line where Mercury is. Next would be the 7-yard line is where Venus is. Earth's on the 10-yard line. Moving out, Mars is 15-yard line. Jupiter is roughly 50-yard line. And then Saturn's the next end zone at roughly the next 100-yard line. Saturn's pretty much the limit of what's nice to look at again in telescopes. I have the computerized telescopes are happy enough to show me Neptune and Uranus, but I rarely look at them because, again, they're just like little dots that turn into a little bit bigger dots. But moving out, if we put Pluto on this, Pluto would be at about 5 AU, or 50 AU, so about at the next 5 football fields away at the little grain of sand grapefruit scale. And that's kind of where astronomical units fail, because if you're talking about things further away than the moon, it's going to be another thousands of these units away that just is going to be really hard to keep straight. If we shrunk down the sun again to be the size of a grapefruit, 2,000 miles away would be the next closest star. Here is Alpha Centauri and Proxima Centauri. So if we had a little grapefruit here, just imagine absolutely nothing until you reach a beach in Belize. That's the scale of our sun and its closest neighbors. We have just a grapefruit here and then absolutely nothing until you reach the grapefruit there. And that's where light years comes into play. So instead of light years as being a distance, I like to think of it as travel time. I feel like that makes it click a little bit more for me. So if instead of astronomical units, this was light years, the sun is about 8 light minutes away from Earth. So the light you see from the sun, the moon is actually about 1.5 seconds away. So the light you see from the moon is left the sun about 8 minutes ago, bounced off the moon 1.5 seconds ago for you to see it. So if we had a light speed rocket ship, we'd be at the sun in 8 minutes, like plenty of time to put on your sunscreen for that trip. If you went out to Saturn, that would be about a light hour away. If you hit bad traffic going to the airport, that's about what the distance of Saturn is for light if you had a light speed rocket ship. Light speed rocket ship, you'd be at Pluto in about 4 hours. So that's like the sand dunes or so, like solid weekend trip, 4 hours, go off to Pluto and come back. But in that same light speed rocket ship, to go to the next closest star to us, to Proxima Centauri there, would be 4 years and 7 months traveling at the speed of light. We don't even have a clue. Unfortunately, actually, most of the things in our sky right now during the fall is all these ones that you probably never heard of that are named all these weird names. Bernard star is actually kind of interesting one, but the next one is Sirius. Sirius is the second brightest star in the sky, second only after the sun, and that's at just under 10 light years away. It's 9.8, I believe, so that's why it's just on the other side of the ring there. Yeah? Is it Pricon?
No, Wolf 359 is
Oh.
a big battle against the Borg.
Oh, yeah? That's where they defend the Borg?
or the,
What was the question?
the galactic year, doesn't Sirius play
So all of these stars are roughly going the same with us. So they'll all rotate around the galactic core in roughly the same direction as us and with us. They definitely do have their own trajectories, so it's not like they're going to stay exactly like this, but they will roughly go with the. Yeah.
That asteroid belt, is that the Earth belt?
This one?
Yeah, where the comets come
No, that's outside of Pluto.
from? Right.
Yeah. What's interesting with the asteroid belt, why I liked that this image had it, is this was actually discovered before they discovered Uranus. Basically, if you take this, you can make an equation that tracks with all of these planets. And mostly it's just you start with 3, and then, or you start with 4, I guess, and then you add 3 for the next one, and then every one from that you double, I think, or I mean, you can see it fairly easily in that Jupiter's about 50 astronomical units out, Saturn's at about 100, Uranus is about at 20. Basically, you double the distance every planet. It gets a little bit wonkier with the inner planets, but every planet is kind of you double distance as it's going out. And they actually discovered, there was somebody that came up with this equation. It's like just how you can memorize the distance of stars to all its planets. Let's see. I think you start with 0, and then you add 4, and then you double it from there. So starting with 0, you'd add 4, get Mercury. I don't know. I'd have to look it up. There's just 3 rules, and if you follow those 3 rules, you can get you can memorize the distance of all the planets from the sun. And when they discovered Uranus, they were like, wait, there's a missing in between, because half of Jupiter would be about 25, and that's not where Mars is. And then later they found Ceres, which is the biggest asteroid in the asteroid belt. And so it's because Jupiter is so big that this isn't that stable of an orbit. This should be a planet. It could be a planet if Jupiter wasn't so big that it tore apart anything in the asteroid belt.
So do we think that that rule is universal enough that it would apply to other solar systems?
So that rule isn't, it's like, it's sort of seen in astronomy as like, it was seen at the time as more like kind of numerology or something, just a strange coincidence. What we learned is it's actually a solution to what's called a Fourier transform, which is basically with math, you can make any wave. Like with a wave, there's going to be stable orbits around the sun. And so it's the equation that the sequence I was talking about is the solution to the Fourier transform for our solar system. But there's a deeper level of math that you have to go to, the Fourier transform, to get to.
The size of our sun?
Yep, yeah, the size of our sun. And again, kind of the 3-body problem with the size of the other planets that are in that solar system. And you can find where stable orbits will be for any given solar system with that. So it's not universal, it's the solution for our solar system, but it's not a universal solution for all solar systems.
Is there any kind of a categorical system for solar systems or various solutions
Um,
you're talking about? Or?
Yeah, there definitely is. I'm not too familiar with it. They do classify different solar systems, usually based on like what's the dominant feature of the solar system. So ice giants, I know, is a big one. There's ones with very few rocky inner planets, but tons of Jupiters and Uranus-style planets out there. I know there's definitely that, but I don't know exactly what the classifications are for each of those. What's super rare about our solar system that we haven't seen in other ones is the moon. Having Earth and the moon be just a quarter of size each other, that size ratio interior is in an interior planet is fairly unheard of, and it's
Technically a double planet system?
no. So the double planet would mean the center of the orbit is outside of the crust of the Earth, which is it's very close, but it's not quite it. But yeah, and all these classifications too and stuff is like everybody trying to put like these big concepts into neat little boxes. The universe never worked like that. That's why we have the whole controversy with Pluto as not being a planet and stuff. Is it's kind of like, is cereal a soup? Like you can make these different little classifications, but like splitting them up, or when you apply them to the universe, it's like a little too messy to like put out like that. This is the scale in the galaxy, and I think I'm going to just skip out to the local group because that's the next like kind of mental picture that I have for a size. So this is the Andromeda galaxy, and this is our Milky Way galaxy. This distance here is 2.7 million light years. So if you ever see the Andromeda galaxy in a telescope or even in a picture, the photons you're seeing spent 2.7 million years traveling all the way across space to land onto Earth and land into your retina or into the camera to capture the image of the Andromeda galaxy. So this is where the light years kind of breaks down. And so my example for this is if you shrunk down the Andromeda galaxy to be the size of a large pizza, it would be a deluxe large pizza with a little fried egg bulge in the middle. Andromeda would be a family-sized large pizza, probably over on the desk over there, a much bigger pizza, again, fried egg bulge. Then these little galaxies they're like satellite galaxies. It's like the moon. They're little galaxies that orbit our bigger galaxy. Those would be like little scones about an arm's length away from your Milky Way pizza.
So where is the Milky Way?
Right here. So Earth is right about here in this little arm of the Milky Way. Then this is zooming out one more level. Earth is just this little arm, and these are all the galaxies that are around us.
So
and
just on the desk, so it's only a few galactic lengths.
yeah, it's really close compared, like relatively, but 2.7 million light years. In actuality, it's yeah,
What's the name over there? Yeah, I can't.
Triangulum?
Yeah.
Is it?
That's what it's called.
Yeah.
Triangulum?
Yep, that's another fairly large galaxy in our local group. This is defined as all the galaxies that are around us that seem to be like gravitationally like linked a little bit.
I was wondering where the closest black hole is.
It's in the core of the Milky Way. The closest known black hole, at least, is in here. There might be another one orbiting around it that might be a little closer. Yeah. You had a question back there? It's a fairly large one. Yeah. Yeah. Yep. Yeah. It's called Sagittarius A star, and that's because it's in the constellation of Sagittarius.
When
Yeah.
we see the Milky Way in the night sky, are we seeing one arm of the Milky Way or the whole disk?
You're seeing basically this disk. So this is across about 100,000 light years, and then this disk is about 10,000 light years thick. And so it's kind of back to the pizza analogy. If you were just one of the toppings on this giant 1,000 light year pizza, you would see some of the toppings below you, some of the cheese and some of the tomatoes and stuff above you, but you wouldn't see that much there or there. If you look out on the horizon of that pizza, along the plane of that pizza, you'd see tons and tons of toppings. So that's why in our night sky, when we see just that Milky Way band, that's because we're looking at the plane of the galaxy. We're looking at it through the edge. So when you look towards Sagittarius is when you're looking towards the heart of the Milky Way galaxy, and then when you look towards Orion, it's called the Orion arm of the Milky Way. That's because when you look out the other direction from the Milky Way, you're looking in towards this part. And that's why back in the slide where I had the Chile observatory of the stars going past it, the southern hemisphere is actually pointed more towards the center core of the galaxy. So that's the brightest chunk of the galaxy. The side we're looking at, the Orion side, is a little bit less bright, but you can still see it there. And how are we doing on time? Do we have time?
Yeah, 5 minutes.
5 minutes. I'm gonna skip this. It's a little movie done by Google. It like zooms out from her and shows the entire universe. It's basically, yep, yeah, it's like that, but it was done by Google Earth. Yeah, I can put it on at the very end here. But I wanted to get to this story because I put on the flyer that this talk will change your life. And this is the story that I think will change your life. So this is the Parkes Observatory, this big dish. It's in Australia. It's most notable for being the observatory that received the message of Neil Armstrong and Buzz Aldrin's first walk on the moon. So Australia got to see that a couple seconds before us because it was theirs telescope that saw it. If you want that story, there's a Australian movie called The Dish, which is just an endearing, like kind of silly little Australian film about them doing that, getting that message. But the story I wanted to tell about the Parkes Observatory has to do with this guy, Prions. I've only read that. What is it? Peritons? It's this mythical creature that's this deer with more like gamey wings or so. But basically, Peritons was what observatories all over the world, radio observatories like this, were calling this very fleeting phenomenon they were seeing in all parts of the night sky of all parts of our universe. They kept getting just these little blips, and they'd just get a little blip and then they'd fix the telescope on there, hoping for another one, and there wouldn't be another one, and they'd move it somewhere else and go take a break, and then they'd catch another blip somewhere else completely, and they had no idea what was going on, what these things were. They were trying to send telescopes to see what was sending out those blips, till the Parkes Observatory looked at the data of their peritons and discovered that it seemed that they happened a lot more frequently around lunchtime. And what was discovered is what those blips are is when you're done microwaving something, you just open the door without pressing cancel. If you open the door while it's still going, it turns it off, but the electrical signal from the sensor seeing that you opened the door to turning it off is slower than the speed of light, and the radiation coming to your food is going the speed of light. So when you do that, it shoots the radiation out from the microwave just for a little blip. It's no health benefits or anything have been seen from avoiding this, but it is something that you can pick up with these very delicate instruments and stuff. And ever since I learned that, it's changed my life, and that I always press the cancel button now on the microwave. So that's how I changed your life with this talk. Oh, the question was how long were they tracking the mystery thing? And I'm not too sure. I'd guess probably like 10 to 20 years. Like it was a common thing, and it's probably wasn't seen that it was when the microwaves came out. Yeah, but I don't know off the top of my head.
Good time for maybe one or two more questions.
Circle back a little bit about flat earthers. I discovered a personal silver bullet for dismissing that.
So I never have engaged with a flat earther directly. I think just because it's just because the thing, just because like flat earthers don't want to come on my program that much. I mean, I'd love to hear the piece and everything. I had a friend that was flat earth curious, and I went on a camping trip with him, and he was telling me, oh, I have this friend, he's a flat earther, and he'll tell you, I'd love to see your dialogue and everything. Later it came out, he asked me if I knew anything about the health benefits of drinking urine, and it turned out this was the same friend, and so I was like, that's not the friend you listen to. And that was the silver bullet to dissuading him from that. Is apparently a fairly big overlap of ones that believe that health benefit and people that believe the earth is flat. So So that's they don't necessarily do that. It's the Coriolis effect. You see it more in bigger scale things like the hurricanes versus cyclones. They spin the opposite direction, but basically it's because the equator is moving a lot faster than the poles. So I said we were going 900 miles per hour to get around the Earth once every 24 hours. If you were on the equator, you're going 1,100 miles per hour to get around the Earth once every 24 hours. That's why we launched the rockets from Florida and now in Brownsville, Texas. Every country that launches rockets tries to do it as close to the equator as possible. So New Zealand does it in their northern island, Japan does it in their southernmost island. Because at the equator, you're going a lot faster. So if you imagine, instead of a sphere, this is a disc like a record player. If you put a little action figure on the edge of that record player, it's just going to fling it straight off of the record player. But if you just balance it right on the spinet, it's going to do a little pirouette. So if you were at the North Pole, that's actually how the North Star works, is the North Star is at a fixed point directly above the North Pole. So if you were at the North Pole, you would just be doing one of these once every 24 hours. So you'd see all the stars circle around your head once every 24 hours because you're not going, once you're at the North Pole, there's no such thing as north or south, or everything's south. There's no such thing as north, east, or west. And so instead of going 900 miles per hour to the east, you just have to do one of those little circles.
Thank you, Luke.
Yeah. Thank you all. I'm certifying you all as stargazers now.
So, besides astrotours.org, how can we follow you or?
I'm doing an Invisible City event. There's flyers in the back there for it. It's at the Invisible City Clubhouse, and I'm calling it Cosmic Odyssey. Basically, I have a bunch of little science demonstration things that I do with the Girl Scouts and the YMCA and the different youth groups we work with, but I wanted to get adults more engaged with it. So there's little stations where you'll do little like cosmic science experiments, and with that there's a whole little gamified thing with it where there's you collect points and there's an award ceremony at the end. And,
Thursday, December 12th?
Yep, 12/12. So it's pretty easy. It's 6 to 9. So
for those of you who don't know, I forgot, I was remiss in saying Invisible City is a social organization here in town, and we have a clubhouse on Santa Fe, and you can go to invisiblecity.com to find that out. So thank you very much for your time. It was really, and I think you could have gone for 3 hours. I think they all would have stayed. So before, for those of you who are Invisible City members, I challenge you to kind of try and host or join me or find me, and let's do some more talks on big ideas in 2025. Because there's a lot of big ideas that we can chase. In the first quarter, we're going to do anatomy and health, and we're going to have a 3-part series on anatomy and health. But for those who are desiring more astrophysics tonight, you can make your way to the Paramount Theater, and Neil deGrasse Tyson is speaking there. I think it's just about to go on right now. A couple people that were supposed to be here actually said, I'm going to go there.
yeah, you didn't say I was competing with.
Yeah, you are. I didn't tell you that.
Oh.
And then for those who are desiring to find out more about the art on the walls, it's actually very fitting. There's a lot of Mayan references here, the Aztec. But there's an artist talk here on Thursday at 6 p.m. With the artist. And so that's a neat event if you want to find out more about the art. And if you want to know more about the cutting edge of rocket ships, on Monday, the window opens for SpaceX to launch their Flight Test 6 of Starship. And it's going to be exciting. Maybe explosions and things of that nature, but it will go up at 4 p.m. Central Time, so 3 p.m. Mountain Time, and you can watch it on YouTube or on X. And I don't know if any of you watched the Test Launch 5. It was amazing. They caught it with the chopsticks. So that's happening on Monday. And then, lastly, next month, I already told you we're going to have one on quantum mechanics. So that'll be on the big, little talks on big ideas. And then Crystal, you have something?
Oh, no, I was just wanting to raise my hand because I would like to.
Oh, okay, cool. Yeah, find me afterwards and we'll figure that out in 2025. So thank you all for coming. Try to keep it to an hour, guys, and have a good time. We can hang out here for another half an hour, mingle, talk to Luke. He's available. Meet Luke's family, meet Luke's sister. And thank you very much.
Thank you.
Thank you. Thanks.
Yeah, nickel. Everyone's going to want to.
Yeah, I need a drink.